3 players, 3 identical decks of cards, numbered 1 to n. N is an integer at least 3. Player A draws 2 cards, no putting back, and writes down the larger number. Player B draws 1 card, returns it to the deck, draws again, and writes the larger of the 2. Player C draws 3 cards, throws away the smallest, and then picks one of the remaining 2 at random and writes it. Everyone is trying to write a big number. They compare papers. Bigger number wins. So who is strongest? Is C's extra card a weapon? Or is that random pick a self-inflicted wound? The author of the source material for this episode admits he could not guess C's strength. By the end, you will not have to guess. The full ranking falls out of the one skill this episode teaches. Here is the whole idea of this episode, in one sentence. The entire difficulty of probability is listing the cases, completely, without overlap, and adding them up. Language compresses many situations into one phrase. The plan works out, hides half a dozen different ways it can work out. Probability punishes that compression. Unfold it, and every problem becomes arithmetic. Even the subject's traditional bogeyman, the recurrence relation, is nothing but a case split on the very last step. What was troublesome is usually, at bottom, trivial. Our whole job is patience. A warm-up in the small. You will send one application to one of 3 companies chosen at random. One of the 3 likes your work already. They accept with probability 4/5. The other 2 are lukewarm. Each accepts with probability 1/4. What is the chance of success? The phrase "the application succeeds" is one phrase, but 2 different stories. Story 1. You happen to pick the friendly company and they said yes. Story 2. You picked a lukewarm one and they said yes anyway. The stories do not overlap, and together they cover everything. So add them. 1/3 times 4/5 plus 2/3 times 1/4. 8/30 plus 5/30, 13/30. Slightly less than a coin flip, and completely settled once the one phrase became 2 cases. What we just used has a name: the law of total probability. Split the world into cases that do not overlap and leave nothing out. Then the probability of any event is the weighted average over the cases. The chance of each case times the chance of the event inside that case, sum. 2 demands and only 2. No gaps, every possibility belongs to some case. No overlaps, no possibility belongs to 2. Miss the first and probability leaks out. Miss the second and you count it twice. All the machinery of this subject, trees, tables, recurrences, is bookkeeping in service of those 2 demands. Now the boogeyman. A coin shows heads with probability 1/3. Toss it in times. How likely is an odd number of heads? Solve it twice. Directly, sum the binomial terms with odd indices. The trick is to expand both 2/3 plus 1/3 to the n and 2/3 minus 1/3 to the n and subtract. The even terms cancel, the odd terms double. The answer, 1/2 times 1 minus 1/3 to the n. Now by recurrence, which is just a case split on the last toss. Odd after n tosses means odd before then tails, or even before then heads. 2 cases, no overlap, nothing missed. That gives the relation Pn equals 1/3 Pn minus 1 plus 1/3, and solving it lands on exactly the same answer. 2 roads, 1 result. The recurrence held no magic. It was the same patient listing in disguise. Now a tournament where every single transition is a third. 3 people play rock, paper, scissors until a single champion remains. Losers leave. A draw changes nothing. First, 1 round of 3 players listed exhaustively. 27 ways to show hands. 9 give 1 sole winner. 9 give 2 winners, who then play on. 9 are draws. A third, and 2 players resolve with probability 2/3, draw 1/3. Now, what is the chance the champion is crowned in exactly round N? List the histories. Route 1, the 3 of them draw N-1 times, then a single winner, that is 1/3 to the N. Route 2, they drop to 2 players at some round K, the pair draws until round N, then someone wins. Multiply along the route and a small miracle. The product is 2/3 to the N, whatever K is. There are N-1 choices of K. Total 2N-1 over 3 to the N. The audit twice over. First, these probabilities must exhaust all histories. And indeed, summing 2N-1 over 3 to the N for all N gives exactly 1. The champion always arrives. Second, a machine ran the exact state-by-state bookkeeping with fractions, no rounding. Round 1, 1/3. Round 2, 3/9. Round 3, 5/27, matching the formula term by term. The source material plays the 4-player version of this game, where the constants are heavier, 13/27 of a draw, a 2-stage descent, and the machine confirms its printed formula the same way. Same skeleton, bigger numbers. Back to the card Duel, with cases as our only weapon. First, each player's score distribution, by counting cases. A writes K when 1 card is K and the other is smaller. K-1 weighs out of N, choose 2. B writes K when the pair of draws has maximum K. Count them. 2K-1 weighs out of N squared. C keeps the card K when the 2 survivors include K. Split by whether the 3rd card was smaller or larger. Count both. And C writes K with probability proportional to K-1 times 2N-K-2. 3 rules, 3 counting problems, 3 explicit distributions. Here they are for a deck of 6, drawn as bars. A leans hardest toward the top. C sags in the middle. The shapes already whisper the ranking. Now we prove it. A against B. Split the event, A wins by A's score. A writes K and B is below K. Sum. Do the same for B wins, and subtract the 2 sums. Everything collapses onto one line. The difference is up to a positive factor. The sum over K of 2 times K-1 cubed, minus K-1, K-2, 2K-1. And that expression simplifies exactly to K times K-1. Never negative, and positive from K equals 2 on. So A beats B. No replacement beats replacement. A against C runs the same rails and collapses to K, times K-1 squared, times K-2, again, non-negative everywhere. A beats C too. Patient case listing, 1 algebraic identity, and the duel is half decided. B against C is the delicate one, and it carries a surprise. The exact difference between B's winning chance and C's comes out as N+1 times N-3, all over 10N squared. Read that numerator. For N at least 4 it is positive, B wins. But at N equals 3, it is 0, not approximately 0, exactly 0. With a 3-card deck, B and C are perfectly matched, case for case. So the full ranking stands. A first, B second, C third. The extra card C draws is real information, but the random pick throws too much of it away. A machine refought every duel by exhaustive enumeration with exact fractions, decks of 3 through 10, every ranking, and that strange tie confirmed. How far does patient case listing reach? As far as probability itself. The two demands no gaps, no overlaps are the entire craft. Trees for small problems, total probability sums for medium ones, recurrences when histories stretch long, all the same act at different scales. And it hands you a habit worth more than any formula. Solve it twice. The coin problem agreed with itself. The tournament formula agreed with the machine's bookkeeping. An episode about counting paths taught the same lesson. When two honest listings of the same world disagree, one of them has a gap or an overlap, and finding it is how you learn. The enemy was never the algebra. It was the case you forgot, and the case you counted twice. One episode, one move. Unfold the phrase. One sentence, several stories, find them all. Weigh and add. The chance of each case times the chance inside it. Trust the recurrence. It is a case split on the last step, nothing more. And when it matters, solve it twice. Agreement is the cheapest proofreading in mathematics. A beats B beats C. The champion arrives with probability 2n-1/3 to the n, and none of it needed brilliance. It needed the patience to list what can happen. No gaps, no overlaps. The rest is arithmetic.